In this video, we're going to go through Chapter 6 of the statistics textbook, which is on measurement error. This is a relatively short chapter, and I'm hoping to be able to get through the entire chapter in one video. And really because I don't feel the need to go through this chapter too slowly, because all of these topics are covered in detail in the measurement and uncertainty playlist. However, don't get me wrong, though, this chapter is still very important, because as we go through this, we're going to want to think about the general statistical techniques that are being applied, which we can extend to any type of scenario, not just measurement theory. Okay, introduction. In an ideal world, if the same thing is measured several times, the same result would be obtained each time. In practice, there are differences. Each result is thrown off by chance error, and the error changes from measurement to measurement. One of the earliest scientists to deal with this problem was Tycho Brahe, the Danish astronomer. But it was probably noticed first in the marketplace as merchants weighed out spices and measured off lengths of silk. Yeah, so we're talking about measurements here, whether it be a measurement with a high-powered million-dollar instrument, multi-million-dollar instrument, or a more basic measurement with a ruler. When they're saying that when you take the same measurement multiple times, it's like statistically impossible to get the same result over and over again. They're talking about from the perspective of if you look at that instrument at its level of precision. So yes, you could get on a scale and you weigh 180 pounds, you get off the scale, you get back on the scale, you see 180 again, get off the scale, get back on the scale, you'll probably see 180 again, of course. But they're talking about if you go down to the precision level of the scale or whatnot, you're going to see 180.232 and then 180.228. There's a degree of uncertainty that comes with any measurement that's ever been taken in the history of the universe and ever will be taken. No measurement we can know with perfect confidence or accuracy. Because in order to do that, we'd have to, if we wanted to weigh something with absolute perfect precision, then we would have to understand, as far as what the reference weight is, we'd have to be able to count every individual atom and then count that every single individual atom has all of its electrons, protons, quarks, etc., which we can't do that. Okay, so there are several questions about chance errors. Where do they come from? How big are they likely to be? How much is likely to cancel out in the average? So chance errors, what they're talking about here is the fact that if we could zoom in on a scale to its level of precision, and we weighed the same thing over and over again, we wouldn't get the exact same result every time. It would be off by, a hundredth of a pound or 5/100ths of a pound or whatever. Okay, so that's what they're talking about, these chance errors. So again, where do they come from? How big are they likely to be? How much is likely to cancel out in the average? The first question has a short answer. In most cases, nobody knows. The second question will be dealt with later in this chapter, and the third question will be answered in part 7. Yeah, so when they say nobody knows, like, where do chance errors come from? I mean, you can come up with certain theories about where the chance errors are coming from, why the scale it weighed, was 100th of a pound different from the previous weight measurement, but you can't say for sure. Was it the electrical circuits? Was it you don't know. So chance error. This section will discuss chance errors in precision weighing done at the National Bureau of Standards. First, a brief explanation of standard weights. Stores weigh merchandise on scales. The scales are checked periodically by county weight and measures officials using county standard weights. The county standards, too, must be calibrated or checked against external standards periodically. This is done at the state level. And state standards are calibrated against national standards by the National Bureau of Standards in Washington, D.C. Yeah, so check out the units and measurements playlist to really get a more full, in-depth description of measurement systems and standards that we compare like weights to or lengths to. I go into this in a lot of detail, and it'll really help your intuition for understanding just like the whole measurement systems and unit systems, what calibrations mean, these comparisons with standard weights, these different bureaus. Okay, this chain of comparisons ends at the International Prototype Kilogram, for short, the kilogram, and actually this has been updated to it's not a actual physical standard anymore, but it used to be. For a while it was the main reference was this International Prototype Kilogram, which was a platinum iridium weight held at the International Bureau of Weights and Measures near Paris. So yeah, again, go check out the units and measurements playlist, because it might be confusing to you. How does this standard reference, how exactly does that work? And we talk about that in detail. It's really interesting. By international treaty, the Treaty of Meter, 1875, 1 kilogram was defined to be the weight of this object under standard conditions. All other weights are determined relative to the kilogram. For instance, something weighs a pound if it weighs just a bit less than half as much as the kilogram. Yeah, so the metric system is kind of the main system that the entire world is trying to adopt. Well, in particular, when it comes to research, science and research. And at the moment, even though, like, for example, the English system is still used in some circumstances in the United States, but what is the case is that there's not multiple master references. The English system doesn't have its own reference for the pound mass, master reference in Washington, D.C. for the pound mass, while the metric system has their master reference for the kilogram in Paris or whatnot. No, the pound is, there's pounds force and pounds mass. The pound mass is just defined relative to the kilogram. So it's based off of the master reference for the kilogram, which isn't the international prototype anymore, but it still references the master reference for the kilogram. The physical, real world, every fundamental unit needs a master reference from nature. To say that a package of butter weighs a pound means that it has been connected by some long and complicated series of comparisons to the master reference and weighs this amount as much. Yeah, this is all really interesting stuff. Go check out the units and measurements playlist. Each country that signed the Treaty of the Meter got a national prototype kilogram, whose exact weight had been determined as accurately as possible relative to the kilogram. These prototypes were distributed by lot, and the United States got kilogram number 20. The values of all the U.S. national standards are determined relative to this kilogram. Yeah, and you can think about how for like a scale you might buy from Lowe's or something, it's not like Lowe's goes travel to Washington, D.C. to reference kilogram 20. Well, no, if a high level of precision isn't required for something like a bathroom scale, well, then there's copies made that they can send out to factories to where you don't have to every single reference doesn't have to go to the master kilogram if you don't need that level of precision. In the U.S., accuracy in weighing at the supermarket ultimately depends on the accuracy of the calibration work done at the Bureau. One basic issue is reproducibility. If a measure is repeated, how much will it change? The Bureau gets at this issue by making repeated measurements on some of their own weights. We will discuss the results for one such weight, called NB10, because it is owned by the National Bureau and its nominal value is 10 grams, the weight of 2 nickels. A package of butter has a nominal weight of 1 pound. The exact weight will be a little different, chance error in butter. Similarly, the people who manufactured NB10 tried to make it weigh 10 grams and missed it by a little. Yeah, so these chance errors can come from anywhere. Maybe the butter, you missed, there's some atoms of butter, right? Butter molecules that just you thought you had the exact same amount of butter, but on a molecular level you don't. Maybe it's coming from the instrument, the electrical circuits or whatnot. So how do we deal with this? We deal with it statistically, which is why we're talking about it here in statistics. All right, NB10 was acquired by the Bureau around 1940, and they've weighed it many times since then. We are going to look at 100 of these weightings. Okay, but they've weighed this weight many times since then. But over time, how do you know that there's not corrosion happening, that atoms aren't in leaping off the weight within humidity, right? There's a lot to think about. We're going to look at 100 of these weighings. These measurements were made in the same room, on the same apparatus, by the same technicians. Every effort was made to follow the same procedure each time. All the factors known to affect the results, like air pressure or temperature, were kept as constant as possible. Okay, so it sounds like they're saying that this NB10 weight was acquired around 1940, and they've weighed it many times since then. We're going to look at 100 of these weighings. So it sounds like these weighings were not on the same day, but they occurred, at different times since 1940. But they've tried to keep the conditions exactly the same every time they did the weighing. And I'm sure they try and keep the weight stored in a controlled environment. But as we go through this, don't get too bogged down with, well, how do you know for sure if you weigh once in 1940 and once in 1950? How do you know if you have to use two different scales, or how do they account for maybe if it corroded a little bit or something? Don't get bogged down with the actual measurement theory here in this video, in this chapter. Go check out the measurement and uncertainty playlist for that. We're really trying to focus on the statistics here. Okay, so the first 5 weighings in the series were these weights. So yeah, if you don't zoom in at a high enough precision, then you're getting the same weight, 9.99 over and over again, right? So you have to zoom in at the precision level. So here's the first 5 weighings. At first glance, these numbers all seem to be the same, but look more closely. It is only the first 4 digits that are solid at 9.999. The last 3 digits are shaky. They change from measurement to measurement. This is chance error at work. And so again, like what we're thinking about here is we're using statistics because, where are these differences coming from? Well, who knows? You could make hypotheses, you could speculate, but I mean, who knows? You do the best you can to keep the conditions the same when you do the measurement and whatnot, but you can't make any definitive statements. But so we deal with issues like this using statistics. Okay, NB10 does weigh a bit less than 10 grams. Instead of writing out the 9.999 each time, the Bureau just reports the amount by which NB10 fell short of 10 grams. So they know it weighs less than 10 grams. So they're going to view this from the perspective of how much less is the weight from 10 grams. For the first weighing, this was this many grams. The zeros are distracting, so the Bureau works not in grams, but in micrograms. A microgram is the millionth part of a gram. Yeah, micro is going to be 10 to the minus 6. So they're going to convert these amount of grams less than 10 grams to micrograms. So you'll move the decimal over 6 spots. So this is 409 micrograms. So here's the first 4 or the first 5 measurements in the amount of micrograms less than 10 grams. All 100 measurements, like put into this form, are shown in table 1. So here we go. These are all the 100 measurements. And again, I know you might be wondering, well, man, how do you analyze this if these measurements were taken at different years past 1940? Don't worry about that. You're thinking about measurement theory there. This isn't inherently about measurement theory. This is more about statistics here in this video. All right, look down at the table. You can see that the results run around 400 micrograms, but some are more, some are less. The smallest is 375 micrograms, the largest 437. So that's the minimum and the maximums. They're all around 400. And there's a lot of variability in between. To keep things in perspective, 1 microgram is the weight of a large speck of dust. 400 micrograms is the weight of a grain or 2 of salt. This really is precision weighing. Yeah, that's amazing. 1 microgram is a large speck of dust. 400 micrograms is the weight of a grain or 2 of salt. Wow. This is very, the range of this is not large weights at all. Even so, the different measurements can't all be right. The exact amount of which NB10 falls short of 10 grams is very unlikely to equal the first number in the table, or the second, or any of them. In fact, we don't know how much it weighs exactly. Only God knows that, the Creator. Despite the effort of making these 100 measurements, the exact weight of NB10 remains unknown and perhaps unknowable. Why does the Bureau bother to weigh the same weight over and over again? One of the objectives is quality control. If the measurements on NB10 jump from 400 micrograms below 10 grams to 500 micrograms above 10 grams, something has gone wrong and needs to be fixed. For this reason, NB10 is called a check weight. It is used to check the weighing process. So what they're saying is that this is really more about their weighing instruments. They're checking the weighing instruments. They know that this NB10 weighs just less than 10 grams, so they check. They'll do these. They'll weigh this NB10 on a certain instrument over and over again just to make sure it's nice and consistent. So that when people come bring in actual weights that need to be calibrated, that they can trust the instrument, the weighing instrument. They just want to make sure it doesn't all of a sudden on one measurement just jump to a certain value that's inconsistent with what they expect. So that's one reason you might want to weigh something or measure something over and over again. You're just checking to see if you're getting a nice consistent uncertainty value and you're not seeing any sudden changes in the measurement, right? If you were taking a temperature reading with a thermal gun, the idea would be maybe you just keep taking the same temperature reading over. If you haven't used the temperature gun in a while, let's say, and you just keep taking the same measurement over and over again, and you're just seeing a nice consistent uncertainty pattern that you expect, and you don't all of a sudden see it just jump 1 degree on one measurement. When you know what the surface of the temperature that you're measuring is supposed to be, around what it's supposed to be. To see another use for repeated measurements, imagine that a scientific laboratory sends a nominal 10-gram weight off to the Bureau for calibration. One measurement can't be the last word because of chance error. The lab will want to know how big this chance error is likely to be. Yeah, so this is probably what we would more commonly think of as a reason for taking repeated measurements. So someone sends off a 10-gram weight to the Bureau for calibration, meaning that they know it weighs around 10 grams, but they want to see, okay, like give us the exact weight. Is it 9.982 grams or 10 point, whatever it is. Okay, but because of chance error, because of the inherent presence of natural presence of chance error, you don't want to just take one measurement, right? You want to take a bunch and kind of like average them out. The lab will want to know how long this chance error is likely to be. If you're taking a really important measurement of something that you want it to be very precise, then one thing you could think you would want to do is take the measurement. Especially if you were recording, a level of precision to where the measurements were varying, like 5.323 and then 5.315, right? Well, what you would do is you take like 50 measurements and average them all out and report the average. Okay, the lab will want to know how big this chance error is likely to be. There's a direct way to find out. Send the same weight back for a second weighing. If the two results differ by a few micrograms, the chance error in each one is only likely to be a few micrograms in size. On the other hand, if the two results differ by several hundred micrograms, each measurement is likely to be off by several hundred micrograms. But you want to weigh it more than twice. I'm assuming they're about to talk about this. The repeated weighings on NB10 save everybody the bother of sending in weights more than once. There's no need to ask for replicate calibration because the Bureau has already done the work. Yeah, so what they're saying is that if you were this laboratory and you sent off a 10-gram weight to be calibrated and you got it back and they told you that, okay, this weight weighs 9.982 grams. That's all they told you. Then you'd say, I wonder how accurate this is, and you'd send it back again with like another name or something. They don't know it's the same weight, and they send it back to you and they say, okay, this weighs 9.993 grams. Well, then okay, now you're starting to get a sense for how accurate what the Bureau is reporting to you is. But obviously you don't do it that way. The Bureau is going to give you this information. They already know the uncertainty with the weight that they're giving you. So you don't need to ask for replicate calibrations. They're going to tell you, look, this is your weight weighs 9.99324 grams plus or minus 0.000 or 320 micrograms or something. So No matter how carefully it was made, a measurement could have come out a bit differently. If the measurement is repeated, it will come out a bit differently. By how much? The best way to answer this question is to replicate the measurement. Yeah, so this is kind of common sense, but you would just want to make sure the conditions are all exactly the same, try and keep everything as, eliminate any confounding variables as much as possible, and then just repeat the measurement and then write down the numbers. And then you'll do statistics on the numbers with this. That's what NB10 is for. So they're going to use all of these measurements here, do statistics on these numbers, and use that to where when they send someone a calibration back, a customer, they can give them an uncertainty of the measurement because of the statistics they did on with these measurements here. And you want to do like 100 of these because maybe the first two are like right next to each other. Oh, so you might think, well, okay, so the uncertainty is really small. It's phenomenal uncertainty. Well, no, but that might have been, you need to take a bunch of measurements, right? If we just looked at the first two measurements here, this was 409 micrograms below, 400 micrograms below. Well, you can't stop there because this suggests the uncertainty is 9 micrograms, but we saw it was the range. This suggests the range is 9 micrograms, but we saw in actuality it was more of on the range of, 67 micrograms, right? But how do you analyze this? To get an uncertainty value, I mean, are you going to look at the average, the standard deviation? So how are we going to look at this statistically? The standard deviation of the 100 measurements in Table 1 is just over 6 micrograms. The standard deviation tells you that each measurement on NB10 was thrown off by a chance error, something like 6 micrograms in size. Chance errors around 2 or 5 or 10 micrograms in size were fairly common. Chance errors around 50 or 100 micrograms must have been extremely rare. The conclusion, in calibrating other 10-gram weights by the same process, the chance errors should be something like 6 micrograms in size. So the standard deviation of a series of repeated measurements estimates the likely size of the chance error in a single measurement. So they're saying we want to look at the standard deviation here for this application. So if we were going to be measuring some 10-gram weight that someone sent in, someone sends in a 10-gram weight to be calibrated, and we measure it and get a measurement, well, using this data here, we would take the standard deviation of this data and use that to make a statement about the error or uncertainty of the measurement we made on that 10-gram weight. So if the machine said the scale said 9.993 grams, then we can say that it's the error or uncertainty in that measurement is going to be around plus or minus 6 micrograms. We would use the standard deviation to make that statement. There's an equation which helps explain the idea. An individual measurement equals the exact value plus the chance error. The chance error throws each individual measurement off the exact value by an amount which changes from measurement to measurement. The variability in repeated measurements reflects the variability in the chance errors, and both are gauged by the standard deviation of the data. Mathematically, the standard deviation of the chance errors must equal the standard deviation of the measurements. Adding the exact value is just a change of scale. Right, so the standard deviation in this case doesn't change because the exact value has been added in. This is just a change of scale. The individual measurement still has this same standard deviation based on the chance error, standard deviation value. Okay, to go at this more slowly, the average of all 100 measurements reported in Table 1 was 405 micrograms below 10 grams. This is very likely to be close to the exact weight of NB10. The first measurement in Table 1 differed from the average by 4 micrograms. So, okay, this is the difference from the average. This is the first measurement minus the average of all the measurements. This measurement must have differed from the exact weight by nearly 4 micrograms. The chance error was nearly 4 micrograms. The second measurement was below average by 5 micrograms. The chance error must have been around minus 5 micrograms. The typical deviation from average was around 6 micrograms in size because the standard deviation was 6 micrograms. Therefore, the typical chance error must have been something like 6 micrograms in size. So, yeah, they're just giving a kind of logical explanation for why the standard deviation is a very good representation for the chance error. Because, okay, so you have the NB10 weight, measured it 100 times, and so we're thinking about its weight in terms of this just micrograms below 9 or below 10 grams. Well, if you take the average of all of those weights, those 100 weights, then that's likely to be close to the actual weight of NB10, as close as we can figure out, right? The average. And with the standard deviation being the most accepted way of quantifying how a set of data is spread from the mean, which they express with this statement here, and that the typical deviation from average was around 6 micrograms in size, because that was the standard deviation, then you can say that the most typical chance error of this measuring instrument, this weight measuring instrument, must have been something like 6 micrograms in size. That's typically what you're going to see as far as how much the measurement is going to vary with this weight measuring instrument based on the 100 measures that they took with this NB10. Okay, of course, the average of all 100 measurements, 400 micrograms below 10 grams, is itself only an estimate for the exact weight of NB10. Exactly. This estimate, too, must be off by some infinitesimal chance error. Chapter 24 will explain how to figure the likely size of the chance error in this sort of average. Interesting. So let's read this again. So we can state that the average of the 100 measurements is likely to be the exact weight of NB10, or at least what they mean by that is if the weighing instrument was perfectly made with no built-in uncertainties. Even in that case, we can't know the exact weight of NB10 because we're not God, right? We don't know if atoms are jumping off or whatnot. But you can think about it like the exact weight that the machine was like intending to output. We can't say for sure. We don't know. We can assume that it's going to be something close to the average. That's a good assumption. But we know that this estimate too must be off by some amount. We don't know it's what the exact weight should have been. And so in chapter 24, we're going to talk about how to figure the likely size of the chance error into this sort of average. So let's really take a step back here for a second and make sure we're clear on what the textbook is trying to convey to us here. Because this really isn't about the science of measurement and uncertainty. What are the statistical principles that we're trying to get from this? Okay, so we've got some measuring instrument, some weight measuring instrument, okay, like a very precise scale. And there's a natural inherent uncertainty in the weight measurements that we're going to get using this scale. We can't know it for 100% certain, any given measurement. Okay, so we're still talking about measurement and uncertainty, weights and measurements here, but try and generalize this summary here to just like any kind of situation, statistical situation. Okay, and so what we're trying to do is we're trying to get a sense for the uncertainty in any weight measurement on this device. So just to keep it simple, we're going to make the assumption that this is a brand new device, and for each measurement, let's say we're doing all of the measurements in the same day, in the same morning or something. It's all temperature controlled. There's no confounding variables. Now you might be thinking, well, but in real life there would be. Well, that we have to learn more statistical methods for that. Well, let's keep it simple here and assume that the environment is perfectly controlled. We're doing all these measurements in one morning, and this is a brand new scale. So what we do is we put the weight on the scale, take it off, put the weight on the scale, take it off, put the weight on the scale, take it off 100 times and record the measurements. So we've got these measurements, and they're all reported as the amount below 10 grams in micrograms. Well, okay, we don't know what the exact weight of the NB10 is, because which one of those 100 is it? We don't know. You might say, oh, we'll go measure it on some more precise device. Yeah, I guess you could do that, but I don't think that's what they're going for here with this example. We're thinking about a situation where we can't know, like we can't figure that out because we're using the most precise scale, or it might be some other statistical situation where you're analyzing a crowd or something, or some information where you can't know. Try and generalize this, okay? So we can make a guess that the actual weight is the average of the measurements, right? Take the average, that's the best we can guess, right? Okay, and when it comes to when we're going to be taking weights of other pieces, other samples, and we're trying to quantify, well, what's the chance error, the uncertainty that we can think about is associated with any future weighings we do on the scale. I know you might be thinking, well, won't we need to update this whole process in like a year when the scale gets older? We're keeping it simple at the moment. Let's assume that the scale is always brand new, nothing changes. Okay, and so we can quantify what we expect to be the chance error on a given measurement using the standard deviation of the 100 measurements. That's like a widely accepted within the statistics community parameter for describing the amount that a data set deviates from the mean, which is exactly what we're looking for here, the chance error. All right, but now what they say is that we'll actually learn a method in chapter 24 that will allow us to factor in the fact that assuming that the actual weight of the NB10 was the average, the fact that there could be some error in that assumption, and we can factor that in. And we'll talk about how we can do that in chapter 24. All right, so again, try and generalize what we just talked about here to any kind of statistical situation. And when it comes to, oh, well, how do we deal with, the device itself has some statistical uncertainty, or, these different other factors, don't worry about that so much. As you progress through this course, you'll learn techniques to where if you were actually studying measurement theory, uncertainty in measurement theory, you would be able to see how you can combine different factors involved in the same system from a statistical standpoint and factor everything in. Okay, outliers. How well do the measurements reported in Table 1 fit the normal curve? The answer is not very well. Interesting. I would have thought that they would be normally distributed because they're just inherently just random. Measurement number 36 is 3 standard deviations away from the average. Number 86 and 94 are 5 standard deviations away. Minor miracles. Yeah, that's the odds of that are low in any circumstance, right? It doesn't matter what the circumstance is. Even if the data is not normally distributed, you don't expect to see data points 3 or 5 standard deviations away from the average. Such extreme measurements are called outliers. And yeah, that makes sense that you're going to label these outliers, and I want to stress this is regardless of whether or not the data is normally distributed or not. In any circumstance, you calculate a standard deviation for a data set that tells you kind of how spread out the data is from the average. Okay, and so if you have data points that are, say, 3 or 5 standard deviations away from the average, well, then what that must mean is that you had a bunch of data points that were grouped in 1, 2 standard deviations away from the average. All of the data points were right around the average, that distance. And then you just had these random points just all of a sudden just jump way out. But if there were a bunch of points that were that far away, well, then the standard deviation would have been bigger. Once you start you can't have a bunch of outliers. That doesn't make any sense, right? It makes no sense to have a bunch of outliers because then the standard deviation would have just gotten bigger to compensate. That's why these measurements are called outliers. They do not result from blunders. As far as the Bureau could tell, nothing went wrong when these 3 observations were made. However, the 3 outliers inflate the standard deviation. Consequently, the percentage of results falling closer to the average than one standard deviation is 86%, quite a bit larger than the 68% predicted by the normal curve. Interesting. So, okay, let's read this carefully. It says, as far as the Bureau could tell, nothing went wrong when these 3 observations were made. However, the 3 outliers inflate the standard deviation a bit, sure. And as a consequence of this, it says the percentage of results falling closer to the average than one standard deviation is 86%, which is quite a bit larger than what the normal curve predicts, 68%. When the 3 outliers are discarded, the remaining 97 measurements average out to 404 micrograms below 10 grams, with a standard deviation of only 4 micrograms. The average doesn't change much, but the standard deviation drops by about 30%. Wow. As figure 2 shows, the remaining 97 measurements come closer to the normal curve. In sum, most of the data have a standard deviation of about 4 micrograms, but a few of the measurements are quite a bit further away from the average than the standard deviation would suggest. The overall standard deviation of 6 micrograms is a compromise between the standard deviation of the main part of the histogram, 4 micrograms, and the outliers. Okay, so this is interesting because once you eliminate the 3 outliers, then the curve comes closer to the normal curve, which is, as I mentioned, that's what you would expect this to be. It's completely random data, it seems. And so when you eliminate the outliers, it says most of the data have a standard deviation of about 4 micrograms, but there are a few measurements that are quite a bit further away from the average than the standard deviation would suggest. Okay, and so, but the overall standard deviation of 6 micrograms for the entire data set was like a compromise between the main data points and the outliers. So if we come back, they're saying, so, okay, you eliminate the outliers, which we justified because when they say that, you know, being 5 standard deviations away from the average is a minor miracle, well, from a probability standpoint, right? Okay, but now you eliminate the outliers and you have more data that's more normally distributed, but you still do have some data points that are kind of farther away than they should be, but it's nothing like these 2 here. Okay, and so that's interesting. The big question is, how do you deal with outliers? Well, it's going to be a judgment call for a specific situation. One of the answers is the more data points you have, the better. Maybe you can quantify the power of an outlier based on how many data points you have that you're working with, in combination with, well, how many standard deviations is it away from the average? You know, 5 is a good bit bigger than 3, so, but it's still going to be a judgment call. You're going to need to be an expert in what you're working on, an expert in your field. If you understand measurement theory really well, then you can make a judgment call, right? In careful measurement work, a small percentage of outliers is expected. The only unusual aspect of the NB10 data is that the outliers are reported. Here's what the Bureau has to say about not reporting outliers. For official prose, the tone is quite stern. A major difficulty in the application of statistical methods to the analysis of measurement data is that of obtaining suitable collections of data. The problem is more often associated with conscious or perhaps unconscious attempts to make a particular process perform as one would like it to perform, rather than accepting the actual performance. Rejection of data on the basis of arbitrary performance limits severely distorts the estimate of real process variability. Such procedures defeat the purpose of the program. Realistic performance parameters require the acceptance of all data that cannot be rejected for cause. So what they're saying here is that the Bureau is, they will most certainly not accept the idea of eliminating outliers. And that makes sense. How could you just eliminate the outlier? Did something happen? Unless you can clearly say that someone bumped the machine. There's just an undeniable external factor that was at play with that measurement, then you can't reject an outlier. However, there are other circumstances where it might make sense to take out the outliers, or maybe like one or two of the outliers. You just have to, it's a judgment call. To me, I'm not a professional in measurement theory. I 100% agree with this. There's no justification you could make for taking those outliers out as far as factoring in the uncertainty of the measurement. Because when someone brings in, sends in one of their weights to be calibrated, well, you could get one of those, large kind of outlier values. Why not? Maybe you would. Who knows? However, if instead of 100 measurements that they did 10 million measurements and there was one outlier, then maybe you could eliminate it then. What if they took 5,000 measurements a day for 10 years and there was one outlier? You had to pretty much win the lottery to get that outlier measurement. Well, at that point, can you say, well, take out the outlier? So there is a hard choice to make when investigators see an outlier. Either they ignore it or they have to concede that their measurements don't follow the normal curve. The prestige of the curve is so high that the first choice is the usual one, a triumph of theory over experience. Yeah, you expect to see that normal distribution for a true random process, and that's what you want to report to your boss, to whoever, right? So just call them outliers. It must have been the air conditioner must have kicked on when we did that measurement. It's an outlier, right? Okay, bias. Suppose a butcher weighs a steak with his thumb on the scale. That causes an error in the measurement, but little has been left to chance. So we're still thinking about this as error, because it's like if we come here, the way we're looking at this is you have a measurement that comes from the scale or whatever. Okay, there's an exact value that we can't possibly know what exactly it is, but just we think about it abstractly, there is an exact value. But how does the actual measurement relate to the exact value? Well, it's the difference between the exact value and what's shown on the instrument is error, right? And so we just talked about chance error, just based on how you can't make a measuring instrument perfect, or you can't make the general environment perfect, but it's still just purely random chance. And now here we're looking at another form of error. Error meaning that a deviation from the exact measurement. If the butcher puts his thumb on the scale, well, then you're not going to be getting the exact weight of the steak because the thumb's on the scale, right? That's going to cause an error. However, we can see this is a bit different than chance error. Okay, it says take another example. Suppose a fabric store uses a cloth tape measure, which has stretched from 36 inches to 37 inches in length. Every yard of cloth they sell to a customer has an extra inch tacked onto it. This isn't a chance error because it always works for the customer. The butcher's thumb and the stretched tape are two examples of bias or systematic error. So yeah, this second example is kind of confusing because then, is that really an error? Because they're intending to add an extra inch or so onto the length of the fabric. So is that really an error, right? Where the butcher didn't mean to put his thumb on it, or is not meaning to put his thumb on it. So, but the whole idea is bias is a deviation from an exact value of a measurement that a measurement should be, but it's not random chance. It's more of systematic. Okay, bias affects all measurements the same way, pushing them in the same direction. Chance errors change from measurement to measurement, sometimes up and sometimes down. So this is a key characteristic that you want to notice between bias and just like chance. Bias, you're going to see every measurement's going to have this same deviation based on the bias. Whereas with chance, it's completely random, above or below what the measurement should be. Okay, so they update the individual measurement equation to where you have the exact value, but then the error is we have bias and chance error. If there's no bias in a measurement procedure, the long-run average of repeated measurements should give the exact value of the thing being measured. The chance errors should cancel out. So yeah, they're saying in a hypothetical, all conditions are perfect. There's, the environment's perfect, and you can take 1 trillion measurements and take out the average. Then if it's purely, there's no bias, it's pure chance errors, then that average is going to be the exact value. If you took an infinite number of measurements, there was no confounding variables except for the brand new machine itself, the brand new instrument itself, then after an infinite number of measurements, you take the average. If they're purely chance errors, then the average is going to be the exact measurement or the exact weight of or whatever of the piece. However, when bias is present, the long-run average will itself be either too high or too low. Yeah, so that's a way you can conceptually think about. You could decompose error into bias and chance. Maybe you don't know if there's bias or not, right? You're trying to figure. You're looking at some error results, and you're trying to separate the bias from the chance. That's how you would figure it out. If you knew the exact weight of something you were weighing, and hypothetically you could take 1 trillion measurements over and over again, then you took the average of those 1 trillion measurements. If there's a difference between that average and the actual weight, then that's bias. Usually, bias cannot be detected by just looking at the measurements themselves. Instead, the measurements have to be compared to an external standard or to theoretical predictions. Yeah, you have to know the exact weight to be able to do this, because otherwise, like you can't be predicting that you think the average weight of something you're weighing should be the average of all the weights. Well, but you can't make a statement about the bias if there's any bias in that case, because you don't know what the exact value should be, the exact weight should be. In the U.S., all weight measurements depend on the connection between K20 and the kilogram. These two weights have been compared a number of times, and it is estimated that K20 is a tiny bit lighter than the kilogram by 19 parts in a billion. All weight calculations at the Bureau are revised upward by 19 parts in a billion to compensate. However, this factor itself is likely to be just a shade off. It too is the result of some measurement process. All weights measured in the U.S. are systematically off by the same tiny percentage. This is another example of bias, but not one to worry about. Okay, so let's read these last few sentences again. So the K20, the U.S.'s copy of the master kilogram, it's estimated that it's a tiny bit lighter than the main kilogram by 19 parts in a billion. All weight calculations at the Bureau are revised upward by 19 parts in a billion to compensate. However, this factor itself is likely to be just a shade off because it too is the result of some measurement process. So all weights measured in the U.S. are systematically off by the same tiny percentage. So that's just another example of bias. So yeah, let's think about what they mean here. Why is this bias? Well, during the time of whenever we were using the International Prototype Kilogram, okay, that's the main reference. We have this K20 copy here, right? But it's really all about the main reference. That's what the exact weight is based on, right? We're looking at an individual measurement is equal to the exact weight plus the errors. So the exact weight is based on the International Prototype. But what they're saying is that K20 is going to be a certain fixed amount off from the International Prototype. And so all of our measuring instruments, since they're calibrated with K20, are going to be this fixed distance off from what the exact weight should be. And that's bias. That's an example of bias.